Welcome to the Explainer. So today, we're going to take a look at a classic piece of 19th century math. And, well, we're going to turn it completely on its head. This is a story about how a fresh perspective can reveal these incredible, hidden structures in something we thought we already knew inside and out.
At the very heart of this whole story is this really mysterious, kind of profound connection between two things in math that seem totally different. I mean, how can something finite, something you can write down completely, be exactly the same as something that stretches on forever?
So, picture this. On one hand, you've got these things called Bernoulli polynomials. They're finite, they're predictable, they're well-behaved. And on the other hand, you have the Hurwitz-zeta function, which is this infinite sum of fractions. Now, a famous identity tells us they are the exact same thing. But the real question, the one that's been nagging people, is why? What's the deep-down structure that actually links them?
All right, so here's our game plan. We're going to start with the puzzle itself, look at the old ways of seeing it, and then we'll pull out this new spectral lens. We'll build a universe where it all works, see the identity in a whole new light, and then get into why any of this really matters.
All right, let's jump right in. This whole puzzle is built around a truly stunning formula, a real gem from 19th century number theory.
And here it is, the Hurwitz-Bernoulli identity. It creates this absolutely surprising link between two worlds that shouldn't really have anything to do with each other. For decades, this formula has been a cornerstone of number theory. We knew it was true, but the why of it all, why did these two completely different worlds line up so perfectly? That was always a little bit mysterious.
So for more than 100 years, mathematicians have known this identity is true. And they've proven it using some really powerful, but let's be honest, pretty complicated tools.
I mean, this story goes back centuries. To prove this, they'd pull out the heavy machinery. We're talking things like complex analysis, which basically means adding extra dimensions to the problem. These methods are, no doubt, incredibly powerful, but all that complexity can sometimes hide the simple, beautiful reason why the whole thing is true in the first place.
But here's the big question. What if we could just strip all of that complexity away and see this identity in a completely new light? Well, this research paper says we can, just by reframing the entire problem.
You see, the key idea here is a total shift in thinking. We're stepping away from those complex functions and into this world of operators. Now just think of operators as simple little machines that take one function and turn it into another. From this new perspective, the identity isn't just some happy accident, it's the direct, almost mechanical result of one of these operators doing its job.
Okay, so to actually use this new lens, we have to build a mathematical universe where it all clicks. So let's see how it's put together, piece by piece.
And it's this really elegant four-step process. First, you take your object. That's the Bernoulli polynomials. Then you put it on a specially designed stage, a weighted Hilbert space. You apply a very simple action. That's the difference operator. And bam, out of that comes a brand new identity.
So let's talk about the stage. This is not just any old mathematical space. It's a custom-built, weighted Hilbert space. You can almost think of it like a theater that's been acoustically designed for a specific performance. That weighting term you see, that's been chosen perfectly so that the Bernoulli polynomials just feel right at home. It makes all the math work out super cleanly.
All right, next up is the action, the forward difference operator. I know, it sounds a little intimidating, but it's actually incredibly simple. All it does is look at a sequence of numbers and figure out the difference, the step from one number to the next. I mean, at its core, it's really just subtraction.
And here's what happens when you put it all together. This is the result. When you apply that super simple difference operator to our Bernoulli polynomials, inside our custom-built space, this is what pops out. This new equation is called the spectral identity, and it's really the heart of this whole new way of looking at things. And the best part, it's all just algebra. No complex analysis needed at all. All right, now this is where we get to the big aha moment. We've got this new, really elegant spectral identity. So how in the world does this get us back to that classic formula we started with?
Well, it all starts right here, with our new discovery, the spectral identity. This is the clean, direct result that pops right out of our object stage action framework.
Next, we use something the author calls the connection lemma. And this part is crucial. This isn't some newfangled idea. It's a classic result, something you'd find in a textbook. Think of it as the perfect bridge, a translator that takes the infinite sum from our new identity
and puts it back into the familiar language of the Hurwitz zeta function.
And just like that, as soon as you cross that bridge, everything clicks into place. The new spectral framework links up perfectly with the classical world, and boom, we get the original Hurwitz-Bernoulli identity back. But here's the thing, we haven't just proved it's true again, we've actually revealed a whole new reason why it's true.
So at this point you might be thinking, okay, that's cool, but why go through all that trouble just to prove something we already knew? And that's a great question. The answer is that this new viewpoint, it's not just some neat academic trick, it actually opens up a whole world of new possibilities.
For starters, it just flat out works, and it works beautifully. Take a look at this table. It shows the values calculated using the new spectral method right alongside the classical formula. And as you can plainly see, they don't just sort of agree, they match perfectly to many, many decimal places.
So just how perfect are we talking? Well, the relative error between the two methods was less than 10 to the power of negative 40. Let that sink in. That is a 0, a decimal point, and then 39 more zeros before you even get to a 1. That level of precision is just astonishing. It proves this new theory is absolutely rock solid.
But what's even more exciting is that this isn't the end of the story. It's the beginning. This whole framework, this spectral lens, could potentially be used to look at other, even more complex and mysterious parts of number theory. Things like Dirichlet L functions or automorphic forms. It's a brand new tool for exploration.
And really, that's the ultimate takeaway here. This new lens isn't just a one-trick pony for looking at a single old identity. As the author points out, it establishes a template, a kind of repeatable method that could pave the way for future discoveries all across number theory.
And that leaves us with one last, kind of mind-bending thought. Just by changing our perspective, by building a new stage to watch an old play, we found a hidden structure that was there the whole time. It really makes you wonder, doesn't it? What other profound connections, what other beautiful truths are just waiting to be found, hiding in plain sight, in the vast, deep universe of numbers?